Hello. In previous slide, we have discussed regarding implementations of any 4-variable combinational logic circuit or Boolean expression using 4:1 multiplexer with the help of LSB 2-variable reduction method. Here I am going to introduce MSB 2-variable reduction method. Here I consider the same problem statement for realizations of 4 input XOR gate using 4:1 multiplexer as a basic building block. So this is nothing but a function tables of 4 input XOR gate. So this is same that we are discussed into previous slide. So instead of AB, that we know that XOR gates having four input XOR gate having 4 input, and 4 input I am going to get represented by variable A, B, C, D. So CD is nothing but my LSB variable of XOR gate, AB is nothing but MSB variable. So here and AF is nothing but the output variable. So previously I am going to map A and B input variable XOR gate with respect to select input pin of 4:1 multiplexer. Here I am going to get map C and D input variable, that is nothing but a 2 LSB variable of 4 input XOR gate. I am going to map with respect to 2 select input of 4:1 multiplexer, that is called as H0 and S1. So here H0 that is LSB select input of 4:1 multiplexer, I am going to map with D variable, and MSB variable S1 of 4:1 multiplexer that I am going to get map with C variable. So here total min terms is 15, 16, start from 0 to 15. So here A, B, C, D input A for XOR gate A, B, C, D 0, 0, 0, output of XOR gate is 0. That we are aware about this function table. So here I am going to get introduce this MSB to variable reduction methods, means I am going to get find out the logic corresponding to I0 data input pin, I1 data input pin, I2 data input pin, I3 data input pins of 4:1 multiplexer, or in other words, data input pin logic with respect to A and B variable, and that A or B variable will be get nothing but most significant bits, means I am going to get fixing the data input pins of 4:1 multiplexer with respect to variable A and B. So that is the backbones of this MSB variable reduction method. So ultimately reducing this variable means I am going to get fixing the data input pins of my multiplexer with respect to these two variable. So look towards carefully this function table of 4 input variable. If I am going to treat that C and D as a select input, so this min term 0, min terms 1, min terms 2, min terms 3, that C and D will be get changing from 0, 0, 0, 1, 0, 1, 0, 1, 1. So these are nothing but 4 select input combinations of your 4:1 multiplexer. If first select input combination is 0, 0, next will be 0, 1, another will be 1, 0 and 1, 1. If select input combinations of 4:1 multiplexer 0, 0, I1 data input, I0 data input pin logic will be transmitted into output of 4:1 multiplexer. If select input combination 0, 1, I1 data input pin logic will be transmitted 1, 0. At that time I2 data input pin logic will be transmitted. C and D becomes 1, 1. I3 data input pin logic will be get transmitted into your output. So I am going to get generating the derived the logic corresponding to data input pins of my 4:1 multiplexer with respect to A and B variable. So here if I am going to consider this select input, so how I am going to get obtaining the logic corresponding to I0 data input pin with respect to A and B variable. If C and D become 0, 0, that will be get applicable to min term 0. Same thing, C and D become 0, 0, that will be get applicable to min terms 4. Again C and D become 0, 0, that will be applicable to min terms 8, and C and D variable will be get 0, 0, that will be get applicable to min terms 12. So ultimately I am going to get merging the min terms 0, min terms 4, min terms 8, min terms 12 into single min terms, and I am going to get able to generating the logic corresponding to I0 data input pins of 4:1 multiplexer. Similarly, if I am going to get merging the min terms 1, min terms 5, min terms 9 and minterms 13, I can generate the data input logic corresponding to I1 and so on. So here I rely on some design method. That design method is similar to the design method that we are going to get explore at the time of LSB to variable reduction method. So I am going to draw one square. Here I can generating the logic corresponding, finding the logic, derive the logic corresponding to I0 data input pins of my 4:1 multiplexer. So this time I can consider eliminating variable is A and another variable as a B. So A can store as a 0 and also A can store as a 1. Similarly B can store as a value 0 or 1. So based upon that, this binary logic, I can divide this square into 4 subgrid. So this is nothing but I am going to able to generate 4 cell. So if A, and according to this table, if A and B become 0 0, at that time output of my 4 input XOR gate becomes 0. So A and B become 0 0, output of my XOR gate becomes 0. Same thing, if A becomes 0, B becomes 1, output of my XOR gate is 1. A becomes 1, B becomes 0, output of XOR gate becomes 1. A becomes 1, B becomes 0, output of XOR gate becomes 0. So here I can generate the logic corresponding to I0 data input pin with respect to variable MSB variable A and B, that is A XOR with B, by grouping this single one and grouping of this single one. For grouping of this single one allows me to generate the A bar, B bar, A, B bar expression. Grouping of this single one allow me the expression A bar, B. So A, B bar plus A bar, B is directly I can write A XOR with B. Similarly, I can obtain the logic corresponding to I1 data input pin with respect to variable A and B. Same thing, A becomes 0 or A becomes 1 or and B becomes 0 or B becomes 1. I can, with the help of this structure, I can generate a logic corresponding to I1 data input pin. If A becomes 0, B becomes 0, at that time output of XOR gate becomes 1. A becomes 0, B becomes 1, output of this XOR gate is 0. A becomes 1, B becomes 0, output of XOR gate is 0. A becomes 1, B becomes 1, output of this XOR gate becomes 1. So I can generate the logic corresponding to I1 data input pin with respect to A and B variable, that is nothing but A XNOR with B. Same thing, I can generate the logic corresponding to I2 data input pin, that is nothing but A XNOR with B, and I3 data input pin logic, that is nothing but A XOR with B. In this way I can implement my 4 input XOR gate using 4:1 multiplexer. For that, so C and D will be treated as a select input, and this I0 data input pin logic, I1 data input pin logic, I2 and I3 I can generate it with the help of this design methodology. So here I can able to generate this logic by merging minterms 0, minterms 4, minterms 8, minterms 12 into and generating one minterm. Similarly, for merging minterms 1, 5, 9, 13, I can able to generating another minterms. For that minterms, we know that C and D variable will be 0 0. For all these minterms 1, 5, 9, 13, C and D variable will be 0 1. Minterms 2, 6, 10, 14, C and D variable is 1 0. Value binary value or binary pattern corresponding to C and D variable is 1 0. Similarly, for minterm 3, 7, 11, 15, C and D variable having binary value is 1 1. So this I am going to treat as my select input combinations 0 0 0 1 1 0 1 1, and according to that select input combination 0 0, I0 data input pin logic will be transmitted, and that will be get transmitted in terms of the variable that I am going to get eliminated, that A and B, means I am going to fixing the data input pin logic I0 with the logic gates of A XOR with B, XOR logic and XNOR logic. So here is nothing but a implementation diagram of implementations of your XOR gate using 4:1 multiplexer. So here I can A XOR with B. I can require two logic gates. One is nothing but XOR and second is nothing but XNOR. So this is the symbol for your XOR, and the symbol for your XNOR is like this. This is the symbol for XNOR. So output of this XNOR will be get connected to I0 data input pin and I3 data input pin. So this will be get connected to I0 as well as I3, and output of this XNOR will be get connected to I1 and I2. In this way I can configure my 4:1 multiplexer can be used as a 4 input XOR gate, A XOR with B, XOR with C, XOR with D. So this S0 S1 is nothing but this is your C and D variable. Now I can apply this AB as a 0 0 and CD is 0 0. At that time F becomes 0. F becomes 0. So this is nothing but the validity of this first min terms. A, B, C, D become 0 0 0, and the output of this design table is 1. Similarly, A, B becomes 0 1. Select input is 0 1. C, D becomes 0 1, and this is 0 0. 0 0 0 1, F becomes 1, and so on. So in this way the multiplexer is a logic element in design of combinational circuit. The two variable reduction method are useful to implement any type of 4 variable combinational logic circuit using 4:1 multiplexer and some logic gates. Thank you.